So here's a good demonstration for you. Last video we talked about angular momentum and torque in terms of rotational units. So we found out that angular momentum is omega, that angular velocity, times your moment of inertia. One thing I wanted to do is, this is what I happen to have around, weirdly. Okay, I have a USB cord. Think of this basically, instead of a cord, think of it as a rod, okay? When you are talking about rotating something, a rod about its end, that rod ends up having a moment of inertia, an I value, right? So for a rod pivoting about its end point, okay, there's the length of our rod right there. In fact, I'm not going to call it capital L, it's just going to be confusing. I'm going to call it cursive L, which totally is not an E. See if I can get even skinnier there. That looks a little bit more like an L. Okay, so the length of the rod about the end, that I for that situation, okay, I for rotating about the end of a rod is 1/3 mr squared. Because remember, it's always that r squared with some kind of a factor before it, right? So if we're going about the end of a rod, we'll get some kind of an angular momentum, right? So let me slow this down so you guys can see that. Hopefully you can see that on the video. You can see this rod rotating about this pivot point, whereas my hand is, right? Now, we said spin axis, okay, about the center, the angular momentum about the center point is always conserved. So what happens if I change, okay, if I change my radius? If I change my radius, I still have to end up with the same angular momentum. It has to be conserved about a spin axis. So if my radius goes from this to suddenly here, what's going to happen? Well, mr squared, right? My mass doesn't change, it can't change, it just is what it is. So if my mass doesn't change here, but my radius does change, the only other option we have to keep this number the same is to change our omega. So again, let me write this out so you can see all the parts that are moving here, okay? So angular momentum about the spin axis, okay, about that, axis of rotation, okay, is omega times, and I'll call it 1/3 because it's a rod, mr squared. If my r changes and shortens down, my omega is going to go up like crazy because this is a squared value, right? So I have to keep this number the same. So if I decrease this value, that value is going to go through the roof. Absolutely huge. So let's go ahead and prove that, shall we? So again, let me start spinning my USB cord again, or aka my rod, okay? So let me see it so it's actually slow enough so you guys can see, but also still keep rotating. Okay, so there it is, rotating, 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 and I'm going to shorten my R and watch what happens. Do you see how that speeds up? Let's do it again. So here it is rotating, right? I'm going to shorten my radius. So if I shorten my radius, what's going to happen to my angular velocity? It speeds up like crazy. And this is the same thing that ice skaters do, okay? When ice skaters are going around and the end of their routine, right? If they go and they spin around like this, right? They're spinning around, around, around. What you'll see them do a lot of times is they'll put their arms in like this, okay? And they'll spin around like crazy. And then when they want to come out of that spin, what do? Well, this effectively right here, that right there, where's their R? Their radial distance, right? And actually, really, if I'm going to be honest about it, it's their center of axis, their center of spin is right there. So their R value is actually just from here to the edge of their arms. That was R, okay? But now, when they want to slow down and come out of that fast spin, what do? They take their arms and they throw them out to the side, and apparently become Stretch Armstrong and have huge arms. But you see that what happens is they change their R value quite a bit, right? So by getting a larger R, right, you get a larger R, you can really take that speed down a lot, because again, this is changing by the square. So if you change that R, you got to change it by the square, and your angular velocity has to change likewise, okay? Because it has to keep the same number here. So, interesting thing. If you have ever noticed that, something going down the drain, you can see this, actually, I think the Dairy Queen that's on Massachusetts, I don't know if you can go in there right now, but later on they have a coin drop, right? A little deposit thing for, I think, St. Luke's or something like that. If you slide a coin in there, it starts going around and circling the drain. You see that as it gets towards the center, it goes really fast because it's maintaining its angular momentum as it's going down that hole and getting a shorter and shorter and shorter R distance. That omega, the angular speed, really picks up as it goes to a smaller and smaller distance. So just because it's so fun to do, let me do it one more time, okay? Look at that. Look at the thing just started whipping around like crazy. All right, so there you go. That's what we got